I was watching the rain the other day, and I found myself wondering, where is all this water trying to go? The rainy season is in full force here. Landslides and floods in the news. Watching the water run down the window, I kept coming back to one small question. Why does water always want to spiral? At the drain, along the river doesn't cut straight. It meanders, curves, bends back on itself. Water seems almost reluctant to move in a straight line. Scientists measure this. The curvature index, the deviation from the straight path, and the number is never zero. It's always something, always a turn. Why is that? I followed the question, and it took me somewhere I didn't expect. Viktor Schauberger, early 20th century Austria, a man who spent years trying to extract energy from the vortices of water. He had no formal scientific training. He was a forest warden, and he learned by watching rivers for a very long time. The scientific establishment largely rejected his theories, but what draws me to him isn't whether he was right. It's the way he asked questions. The thing that held his attention was the temperature of 3.98 degrees Celsius, the precise point at which water is at its most dense, its heaviest. Now, why would water behave that way? Most liquids simply get denser as they cool, straightforward thermal contraction. But water does something odd near 4 degrees. It reaches a peak of density, and then, as it cools further toward freezing, it actually becomes lighter. Not heavier, lighter. This is established physics. As water cools, two competing forces come into tension. The first is thermal motion, which pushes molecules toward a tight, compact arrangement, collapsing inward. The second is hydrogen bonding, which pushes outward toward more space, toward the open, lattice-like structure of ice, expanding. At 3.98 degrees, these two forces are exactly balanced. Below that point, the ice-like structure begins to win. Water expands, grows lighter. That balance point is also the reason lakes don't freeze solid in winter. The densest water sinks to the bottom. Fish survive in that cold, still layer. The whole system is held alive by that one quiet tipping point. That's the established science. Now here's where things get interesting. A researcher at the University of Washington, Gerald Pollack, observed something that doesn't fit neatly into standard water chemistry. When water comes into contact with a hydrophilic surface, a surface that attracts water, it forms a distinct region along the boundary. He called it the exclusion zone, or easy water. This zone excludes solutes, behaves differently under light, and creates a kind of charge separation, almost like a microscopic battery that can be charged by light. The scientific community hasn't fully settled on what to make of this. But when Schauberger said water was alive, I wonder if what he was seeing, in the streams and rivers he watched so carefully, was something like this. A sensitivity in water that we're only beginning to describe. And then there's a more speculative step. A hypothesis proposed by Italian physicists Giudice and Preparata. They suggested that liquid water at room temperature spontaneously forms what they called coherent domains. These are regions roughly 100 nanometers across. In them, water molecules oscillate in quantum unison, phase-locked with a trapped electromagnetic field. Giudice and Preparata estimated that at any given moment, around 40% of water exists in this coherent, dancing state. The other 60% drifts, unorganized. And the two are in constant, dynamic exchange, molecules slipping in and out of the dance continuously. Mainstream physicists are skeptical. Thermal noise, they argue, would destroy any such quantum coherence almost instantly. But the image stays with me. At any moment, some portion of the water is moving in perfect step, and the rest is just floating. Who is dancing and who is watching? That's only decided in the instant itself. If water carries a faint record of its surroundings, of temperature, geometry, contact surfaces, the shape of the space it moves through, can we call that memory? Or is it something more like the way a mirror holds an image only while you stand in front of it? I'm not sure, but I find the question worth sitting with. Before we get to the locusts, there's one more detour I'd like to take. Viktor Grebennikov, a Soviet entomologist. He claimed that the microscopic cavity structures on the undersides of beetle wing covers, a periodic lattice of tiny holes, produced anomalous effects. sensations, and eventually he wrote a kind of levitation. No controlled experiment has replicated this. No peer-reviewed physics supports it. By any scientific standard, the claim doesn't hold. And yet, the underlying intuition, that structure itself could bend or redirect physical laws in unexpected ways, has turned out to be true, just not in the way Grebennikov described. Acoustic metamaterials are engineered structures where the periodic arrangement of components gives the whole material an effective mass density that can be negative, meaning when you push it, it moves toward you rather than away. This isn't metaphor. It's been derived mathematically and confirmed experimentally. Structure can reverse the apparent direction of mass. And at the quantum scale, there's the Casimir effect. Two metal plates, brought within a few nanometers of each other, experience a force generated from the vacuum itself, from the constraint that the space between the plates places on quantum fluctuations. In certain configurations, this force becomes repulsive rather than attractive. Some physicists have taken to calling this quantum levitation. Grebennikov was wrong about the mechanism, but the direction his intuition pointed, towards structure as something that interacts with fundamental forces in non-obvious ways, turned out to be a real direction in physics. A wrong answer can point toward a right question. I find that oddly reassuring. Schauberger believed that applying a right-handed spiral to water at its optimal density would release something, some form of energy he couldn't quite name. The rightward turn, it appears repeatedly at very different scales. Look at the crown of a newborn's head. The hair forms a cowlick that in most people spirals clockwise. The double helix of DNA spirals in a right-handed direction. The arms of spiral galaxies, when you trace the direction of their rotation, turn the same way. These are not the same phenomenon, but there seems to be something in the architecture of the universe that encodes information by turning to the right. Did human beings know this, in their bodies, before they could explain it in words? In Buddhist and Hindu traditions, circumambulation, walking in a circle around a sacred object, proceeds clockwise. The right hand stays toward the center. The movement aligns with the apparent motion of the sun across the northern sky. The Sanskrit term is Pradakshina. It is understood as a movement of construction, of building order, tightening. Islam's Tawaf, the ritual circling of the Kaaba in Mecca, goes in the opposite direction. Counterclockwise, the Kaaba is kept to the left. This surprised me when I first looked into it, but it begins to make sense when you read it as a different kind of movement. Not construction, but return, release, the loosening of a thread rather than the tightening of one. What the anthropological literature shows, regardless of direction, is that synchronized collective movement does something to us physiologically. The French sociologist Durkheim called it collective effervescence, the dissolution of individual boundaries through shared physical action. Studies of crowd dynamics confirm that patterned, synchronized movement in dense groups creates emotional coherence, increases endorphin activity, and produces a felt sense of unity that outlasts the movement itself. The universe tightens the spiral rightward. It unwinds it leftward. And perhaps every religious tradition that organized itself around a circling body of people was encoding that rhythm, the breath of contraction and release, into collective memory. Now, what happens when that rightward tightening reaches its limit? The desert locust gives us, I think, the clearest available answer. Schistocerca gregaria. When population density crosses a certain threshold, something changes in these insects within hours. The trigger is mechanical. The hind legs are brushed repeatedly by the bodies of nearby locusts. That tactile stimulation travels through the nervous system to the metathoracic ganglion, a cluster of nerve tissue in the thorax, the insect's central processor for exactly this kind of signal. And it triggers a cascade of serotonin, not a gentle rise, a surge. Within hours, the animal's behavior, morphology, and endocrinology begin to shift toward the swarming state. The engine that keeps those swarms moving, it turns out, is not food. It is fear. Locusts cannibalize each other. The insect behind you is a threat. The only escape is to keep moving forward. Flight becomes forward motion. Fear produces order. There is something there worth pausing on. How much of what looks like collective purpose is actually individual avoidance, compounded? But there is a second mechanism, and it operates on a much slower timescale. A pheromone called 4-vinylanisolol, or 4-VA, produced by gregarious males, accelerates sexual maturation in females. It stimulates the biosynthesis of juvenile hormone, bringing late-developing females into synchrony with their more advanced peers. The result is that enormous numbers of females lay their eggs within a very narrow window of time. The next generation is born already dense. If serotonin is the fast clock, switching individual insects into swarm mode within hours, then 4-VA is the slow clock, synchronizing the reproductive schedules of millions across weeks. And when both clocks are running in phase, the swarm becomes self-amplifying. Researchers describe this high synchrony state as simultaneously very powerful and very fragile. Why fragile? Because everything supporting it depends on density, serotonin production, pheromone concentration, the cannibalism pressure that keeps locusts moving forward. Drop the density even slightly, and each of these feedback loops begins to reverse. And then there's a third actor, a microsporidian parasite, Paranosema locustae, which spreads by contact. It inhibits the transition to gregarious behavior and interferes with the neuroendocrine pathways the swarm depends on. Here is the terrible elegance. The parasite spreads most effectively at exactly the density levels the swarm has created. The swarm plants the seeds of its own dismantling. When it falls apart, it does not fade slowly. The serotonin feedback, the pheromonal synchrony, the pathogen load, they reverse together, cascading. Scientists call this a cascade collapse. The swarm doesn't diminish, it disappears. When a system's information load exceeds what it can process, the system resets. This pattern, a peak of density followed by sudden collapse, appears in human history as well, often framed as myth. Atlantis drowned at the height of its power. But I'd rather look at the measured data. Jakarta, Bangkok, Venice, New Orleans. Around the world, major cities are sinking, not metaphorically, physically. Ground subsidence driven by groundwater extraction, hydrocarbon removal, and the sheer weight of built infrastructure. Parts of Jakarta have been recorded sinking at roughly 25 centimeters per year. Venice has lost more than 2 meters of elevation over the past century. A 2025 review in Nature noted that the most dangerous characteristic of land subsidence is its lag time. Damage accumulates invisibly for decades, and by the time it becomes visible, the sunk cost of built complexity makes adaptation extraordinarily difficult. The very act of building, the accumulation of infrastructure, the extraction of resources needed to sustain density, undermines the ground on which the building stands. Historian Joseph Tainter argued in 1988 that civilizations collapse not from external assault, but from the internal logic of complexity. Every problem a society solves, it solves by adding complexity. In the early phases, each unit of complexity delivers high returns. Then those returns begin to diminish, and eventually you reach the point of negative returns. The cost of adding one more unit of complexity exceeds the benefit it provides. When that happens, the system can no longer sustain itself. It simplifies rapidly. The historian Peter Turchin has built quantitative models, what he calls cliodynamics, tracking population, elite overproduction, inequality, and state fiscal capacity across centuries. His models suggest these variables move in cycles, converging periodically at structural crises with roughly generational timescales. Neither Tainter nor Turchin uses the word entropy, but the structure they describe is the same. Collapse is not decline exactly. It's a phase transition, from a low entropy, highly coordinated state to a higher entropy, less organized one. Think of a screw. Turn it to the right and it advances, pulling matter together, increasing density. But over-tighten a screw and the threads strip. All the turning becomes rotation without traction. Empty motion. The screw spins, but nothing moves. You are at the limit of the right-handed turn. What Tainter calls diminishing returns on complexity. That is the moment just before the threads give. I think we are somewhere near that point. Information accumulates faster than it can be processed. Networks of interdependence grow more intricate. Cities add density. And, as with the locust swarm, when density passes a certain threshold, the feedbacks that sustain the system begin to change sign. The conflicts over territory and resources that mark our current moment, I'm not sure they're really about what they claim to be about. When locusts swarm, they are not moving toward food. They are fleeing the locust behind them. The movement looks purposeful. It is, in a deep sense, the opposite. And so perhaps, when the spiral has tightened past the point it can hold, what is needed is the other movement. The counterclockwise turn, not collapse, release, the loosening of the thread. The quiet interval between one configuration and the next. Gerald Pollack's exclusion zone water forms only at a boundary, only when water meets a hydrophilic surface. Without that contact, the ordered zone doesn't exist. There is only bulk water, drifting. The water's capacity to hold structure depends entirely on what it touches. Stillness at the surface. Contact with something that isn't moving. Perhaps something similar is true for us. The capacity to retain and transmit what matters, to let what has accumulated actually settle into form, requires a surface. Stillness. Contact with something that isn't moving. If the swarm dissolves, if the complexity reduces, if there is a period of quiet, the information doesn't vanish. It waits, encoded in simpler structures, until conditions allow it to organize again. That is, in any case, what water seems to suggest. Tonight, if you have the chance, watch which direction the water spirals as it drains. And the next time you turn a screw, clockwise, tightening, notice the small resistance in your fingertips. The tension of material meeting its limit. In that small gesture, if you're willing to entertain it for a moment, the whole drama of a universe building itself up and letting itself fall is somehow present. I find that worth thinking about. That's all for today. The rain is picking up. I'll talk to you again next time. This is Kaide, out.